Let us understand nuclear energy. Energy can be released if less tightly bound nuclei are transmuted into more tightly bound nuclei. Two such processes by which we can do so are fission and fusion. These processes produce much larger amount of energy as compared to conventional fuels. Energy produced by fission of 1 kg uranium equals to energy produced by burning 10 million kg of coal. The number of free neutrons multiplies as they strike the uranium element, and this continues till the last uranium element left. Such a reaction is uncontrolled nuclear fission. This is used in nuclear bombs. Besides this, there is controlled nuclear fission, which is used in nuclear reactors. Let us study about fission. When a neutron was bombarded on a uranium target, the uranium nucleus broke into two nearly equal fragments, releasing great amount of energy. The reaction representing is 1 neutron plus 235 U92 goes to 236 U92, which goes to 144 Ba56 plus 89 Kr36 plus 31 neutrons. Fission does not always produce barium and krypton. 1 neutron plus 235 U92 goes to 236 U92, which goes to 133 Sb51 plus 99 Nb41 plus 41 neutrons. The energy released, that is the Q value, in the fission reaction of nuclei like uranium is of the order of 200 megaelectron volts per fissioning nucleus. Let us study about nuclear reactor. Following series of reaction take place in a nuclear reactor. 238 U92 plus 1 neutron goes to 239 U92, which goes to 239 Np93 plus electron plus neutrino. 239 Np93 then goes to 239 Pu94 plus electron plus neutrino. It was discovered that neutrons liberated in fission of a uranium nucleus were so energetic that they would escape instead of triggering another fission reaction. Also, it turns out that slow neutrons have a much higher intrinsic probability of inducing fission in 235 U92 than fast neutrons. These neutrons, unless slowed down, will escape from the reactor without interacting with the uranium nuclei unless a very large amount of fissionable material is used for sustaining the chain reaction. When 235 U92 undergoes fission after bombarded by a neutron, it also releases an extra neutron. In fact, on an average, 2.5 neutrons per fission of uranium nucleus are released. The fact that more neutrons are produced in fission than are consumed raises the possibility of a chain reaction with each neutron that is produced triggering another fission. The chain reaction can be either uncontrolled and rapid or controlled and steady, as in nuclear reactor. The average energy of a neutron produced in fission of 235 U92 is 2 mega electron volt. These neutrons, unless slowed down, will escape from the reactor without interacting with the uranium nuclei unless a very large amount of fissionable material is used for sustaining the chain reaction. The essential components of a nuclear reactor are the core, metal rods containing enough fissionable material to maintain a chain reaction at the necessary power level. As much as 50 tons of uranium may be required. A source of neutrons to initiate the reaction, such as a mixture of polonium and beryllium. A moderator to reduce the energy of fast neutrons for more efficient fission. Materials such as graphite, beryllium, heavy water, and light water are used. A coolant to remove the fission-generated heat, water, sodium, helium, and nitrogen may be used. A control system such as rods of boron. Let us know more. Multiplication factor. The ratio K of number of fission produced by a given generation of neutrons to the number of fission of the preceding generation. For K equals to 1, the operation of the reactor is said to be critical, which is for steady power operation. If K becomes greater than 1, the reaction rate and the reactor power increases exponentially. Unless the factor K is brought down very close to unity, the reactor will become supercritical and can even explode. Control rods. The reaction rate is controlled through rods made out of neutron-absorbing material such as cadmium. They are called control rods. In addition to control rods, reactors are provided with safety rods, which when required can be inserted into the reactor and can be reduced rapidly to less than unity. Huge amount of energy can be released if two light nuclei combine to form a single larger nucleus. This process called nuclear fusion. Some examples are 1H1 plus 1H1 goes to 2H1 plus positron plus neutrino plus 0.42 mega electron volts of energy is also released. 2H1 plus 2H1 goes to 3He2 plus 1 neutron plus 3.27 mega electron volts of energy is also released. 2H1 plus 2H1 goes to 3H1 plus 1H1 plus 4.03 mega electron volts of energy is also released. Such a process is hindered by the Coulomb repulsion that acts to prevent the two positively charged particles from getting close enough to be within the range of their attractive nuclear forces and thus fusing. The height of this Coulomb barrier depends on the charges and the radii of the two interacting nuclei. To generate useful amount of energy, nuclear fission must occur in bulk matter. What is needed is to raise the temperature of the material until the particles have enough energy due to their thermal motions alone to penetrate the Coulomb barrier. This process is called thermonuclear fusion. The energy generation in stars takes place via thermonuclear fusion. Quite large distance for nuclear forces to act. Provide enough heat combining and becoming 2H1. The nuclei fuse because of sufficient thermal energy. Fusion reaction yield more energy per nucleon than fusion. Overview of fusion. Fusion reaction yield more energy per nucleon than fission. 2H1 plus 2H1 goes to 3H1 plus 1H1. 3H2 plus 2H1 goes to 4He2 plus 1H1. Fusion reaction yield 18 mega electron volt of energy from 5 nucleons, whereas fission yields 200 mega electron volt from 236 nucleons. Fission results from a neutron striking an atom. The atom in turn momentarily absorbs the neutron before splitting into two or more fragments. An important product of fission process is the energy release, which is approximately 200 mega electron volt. In addition, two or more neutrons are also liberated due to fission. The neutrons are intended to create a chain reaction, that is, another fission. The neutrons released from fission continue to produce another fission, and so on. Controlled thermonuclear fusion. The first thermonuclear reaction on Earth occurred at Annie Wettock et al. On November 1st, 1952, when USA exploded a fusion device generating energy equivalent to 10 million tons of TNT. 1 ton of TNT on explosion releases 2.6 multiplied by 10 raised to the power 22 MeV of energy. A sustained and controllable source of fusion power is considerably more difficult to achieve. It is being pursued vigorously in many countries around the world, including India, because fusion reactor is regarded as the future power source.